sample means, when we're talking about sample means, we're talking about many samples of the same size from the same population averaged together, or the mean. We've kind of talked about this already, but it's worth noting again. And our notes are pretty short today, but pretty important. This is a big idea today, and I've kind of addressed it a little bit the other day. So the first thing that we want to know is, what's mu sub x bar? Well, what this is this is the average, the mean of many sample means. Okay, the average of many averages. Okay, sample averages. So I've been kind of prepping this for a while now. We'll see if you guys are getting it yet. The other day I talked about finding the average age of everybody in the class, and I said I could do it a couple different ways. I could just ask everybody and average that, right? That would be taking a census of the class and getting an average. Or I could take smaller groups, and I suggested taking 3 at a time and finding the average age of 3 here and 3 there and 3 there. Keep taking groups of 3 until I've taken many, many groups of 3 and many averages. And what am I going to get with those groups of 3 averages if I average all of those averages? Well, average age of the class, right? Isn't that the parameter? So mu of many samples, the average of many samples equals the average of the population, the mean of many samples. Of the same sample, or same size from the same population. That's important. Equals the mean of the population. And be clear, today we're talking about counts. We're back to counts. We did proportions for a day, and now we're back to counts. So we're talking hard data, not percentages. The other one that you need to know is this guy. Sigma x bar. This is the standard deviation of many sample means. So it's taking the standard deviation of this 3 and the standard deviation of that 3 and the standard deviation of that 3 and keep taking those standard deviations and then averaging them. And this is one of the easiest standard deviation calculations there is in all of statistics. It is simply sigma over the square root of n. How many people are you sampling? Any idea why we would divide that by the square root of n? I'm betting you know it, you just don't know you know it yet. So what happens when I increase the sample size? What happens to the width of our normal curve, assuming that we have a normal situation? If I increase the sample size, the curve does what? It gets taller, and because it gets taller, it has to get narrower, right? Because it still has to have an area of 1. So if I had something like n equals 1 and a normal situation, that's maybe going to look like this. But if I change that to n is greater than 1, let's say n is 10, that's going to change that. It's going to narrow it up and make it taller. So what this dividing by the square root of n does is it adjusts the width of the standard deviation for the number in the sample. Adjusts the width of your distribution based on sample size. And what this leads us to now is a new standardizing formula. Or maybe a slightly modified is probably a better way of putting it. Not so new. And that being, instead of, well, what we've done in the past has been x minus mu over sigma. Well, now what we're looking at is many samples. So it's going to be the average, or more than one in a sample, becomes x bar. And so now that we're talking about more than one, we have to also adjust for the width that's going to change. So it's going to change our normal curve by the square root of n. Now, technically, this has always been here. We just don't write it because if it's just x, that's 1. So the square root of 1 is just 1. So you're dividing by 1. It doesn't change anything. But technically, we've had this all along. It's just that n's been 1, so it wasn't necessary. And this equals z, which we then take to table A. So shall we look at an example? Okay. Let's take the SAT as an example. Has everybody got this down? So, SAT scores. Let's say an individual scores 1250. Not a bad score, right? It's not going to get you into Ivy League, but it's not a bad score. The mean of all students who take the SAT is 1060. And the standard deviation is 195 points. Okay. So let's take a look at how many standard deviations away from the norm is this individual? By the way, you can do this. These numbers are correct, you know, if you know your own SAT score. How far away from the norm are they? So we'll find out the z-score, and then we'll see what's their percentile. So this is just going to be x minus mu over sigma because we're talking about an individual. So no change in this one. 1250 minus 1060 divided by 195. That's going to be 190 divided by 195, which is about 0.97. And if we go to table A and look at 0.97, that gives me a probability of 0.8340. So this person at 1250 would be in the 83rd percentile of all test takers for the SAT. Not bad, right? The top 16.6%. Person's in the top 16%, not too shabby. Now, let's change the question. Let's say we want to know what's the likelihood that a randomly selected group of 5 will have an average of 1250 or more. Do you think that's going to be higher or lower than this? Well, let's see. So what's the probability? Let's say SRS of 5 is greater than 1250. Their score is greater than 1250. That's not written real well, but that's the idea there. So now we have n equals 5. And everything else is going to be the same. We'll use the 1250 and the 1060 and the 195, but this is going to be x bar minus mu over sigma divided by root n, because we're talking about more than one. So that's going to be still 1250. That's the number we want to compare, minus 1060 divided by 195. But now I've got to divide this by the square root of 5. Let's see what that gives us. So I know that's 190 divided by that's a little bit larger z value. So z is 2.18. So if I take that to table A, 2.18 is 0.9854. So what that would do is that would say that this randomly selected group of 5 would be in the almost the 99th percentile of all randomly selected groups of 5 that I could possibly select from. So it's pretty unlikely that I would get a group of 5 that would be this large or more. So the probability of getting that group of 5 is going to be 1 minus the 0.9854, which is going to equal 0.01, what is that, 46, I think. So that would be the probability of picking a random group of 5 that would average 1250 or more. Why? Because we're narrowing it up. The larger your sample size, the less likely you're going to be very far away at all from this mean. Most groups of 5 would fall very close to this 1060. What if we go to 10? What do you say? How likely do you think it would be to get 10 people randomly selected to have a SAT score, an average SAT score of 1250 or more? If this one's that, the next one's going to be probably really small, huh? Let's see. So let's say n equals 10. I'm going to cheat here. I'm just going to take what I have in the calculator and copy it and change the 5 to 10. Is that cheating? I didn't think so. 3.08 is the z-score. So if I go to my table A again, it's not off the charts, but it is 0.9990. So if you could find a group of 10, if you could randomly select a group of 10 that had a score this high, they would be 1 in 10,000. The probability of that would be 1 in 10,000. So it's not all that uncommon to be able to randomly select somebody with a relatively high SAT score. But it's really uncommon to find a group, if you're randomly selecting, that would have a high SAT score like this. So my daughter's smack dab in the middle of this. She's a junior. She just took her first SAT and her first ACT, and they came out pretty good. Not quite Ivy League good, but like maybe within striking distance. So now she's starting to think Ivy League, and I'm going like, how would my genes be able to have any input for a kid that would get into the Ivy League? I can't imagine. She must have gotten like 3 for me and 10 trillion from her mom or something like that. I don't know. So. All right. Yeah, let's have a look at one of the problems. I think I did a problem in the book, but I didn't attach it to this. Let's see. I think we're looking at page 479. Yeah, let's look at songs on the iPod. I'll write this down here in just a second, but this problem says that David's iPod has about 10,000 songs. I'm thinking David's pretty serious about his music. The distribution of play times for these is heavily skewed to the right, with a mean of 225 seconds and a standard deviation of 60 seconds. Suppose we choose an SRS of 10 songs from this population and calculate the mean playtime X bar of these songs. Okay, I'm going to take some notes here. number 53. Page 479. So we've got 10,000 songs. Let's see. It is skew right. Let's talk about that for a second. Why might this be skew right? I'm talking about the length of songs. What's the shortest song you can imagine? In general, the shortest songs that I can imagine are all punk songs. Punk songs, usually if you have a 2-minute song, it's long. Or if it's a 3-minute song, it's like really out there. Okay. So I'm going to say some of the shortest songs are just under 2 minutes, probably. What about the longest songs? Yeah, like Stairway to Heaven or what's that Queen one? Bohemian Rhapsody, right? That's a pretty long one, right? So there's going to be some long songs that are going to take and draw this out. So this skew right kind of makes sense to me because you're going to have most of your songs are going to be right in here, but then your Bohemian Rhapsody is going to be out there quite a ways. And Rush did a song that was 21 minutes long, and one of my students in the last class calculated that that was like 17 standard deviations away from the norm. So it does happen to be that far out. It's just not that common. Okay, so we've got 10,000 songs. The average is 225 seconds with a standard deviation of 60 seconds. How do I know that that's mu and not x bar? And how do I know? What's that? Exactly. It's a population value. Yeah, it's actually population value. Population of the songs on his iPod. And we're going to pick 10 songs. Identify the mean of the sampling distribution of x bar. The mean of the sampling distribution of x bar is mu sub x. And what did we say in our notes that mu sub x equaled? Mu. It's 225. Yeah. So that means if I take many, many samples of size 10 and average those averages, I will get the population average. Okay. And B, calculate and interpret the standard deviation of the sampling distribution of x bar. Verify that the 10% condition is met. Let's do that first. 10% condition is 10% of the population bigger than 10. % of 10,000, is that bigger than 10? Yeah, that's 1,000, isn't it? Yeah, definitely. So we've met our 10% condition. This is met. And now we want to figure out what's sigma x bar. So that's going to be sigma divided by the square root of the sample size. So in this case, sigma is 60 divided by the square root of 10. Oops. About 18.97. Or about 19 seconds. And that was the only one I was planning on going through with you. That little algebra practice thing that we did should maybe kind of help you with 55. I'll let you give those a go, and I'll come around and help out once I take roll.